Good morning. In sections 17.4 and 17.5, we're going to consider two loosely related topics. The first is the subject of cryptography, which continues the discussion of codes, and in particular, the characteristic of a desirable code that it preserve confidentiality, that only those who are entitled to listen to the message are able to do so. Then in section 17.5, we're going to consider computer logic or digital logic, and this is behind much of the logic of web searching and the logic that computers themselves use to communicate. In both cases, the coverage that I'm giving here may not be as close to the textbook as is typically the case, so I would encourage you to look to these notes for my indication of what is most important and what you would be held responsible for on the test. First, regarding cryptography, here's a very common situation. Two people want to communicate. So you can see why I'm a math major instead of a art major. And believe it or not, you can look up papers in the subject of cryptography, scientific papers, and find out that it's pretty standard to name these people Alice and Bob. And Alice and Bob want to talk, but they have a problem. Their problem looks like this. This person is named Eve, and the reason Eve is a problem is that she has very large ears. Very large ears. And so as Bob and Alice want to communicate, Eve, which stands for eavesdropper, is trying to listen in, presumably with hostile intent, or at least has no business in hearing the conversation between Bob and Alice. And so Bob and Alice want to set up a code, a cryptographic code, so that Eve is not able to detect what is being said. This problem, of course, is an old one. We have records going back to the time of Christ that Julius Caesar, the emperor of the day, Roman emperor of the day, wanted to communicate with his generals, and of course he didn't want the enemy forces knowing what strategies he was conveying to them. And so a technique that Caesar himself used briefly, apparently, was the so-called Caesar cipher, where you take each letter and you replace it by the letter plus 3 when the letters are numerically coded as per this table, and then you mod by 26. Let's look at an example. This is from my own second and third grade days. Maybe you had the same experience as I, where you were here and there was some person over here of the opposite gender whom you wanted to get the attention of, and so on a little slip of paper you'd write some suitable message and pass it over, and then maybe on the slip of paper you'd put a space for a response and hope to get one back. Or maybe second graders don't do that anymore. I don't know. First step would be to convert this to the numerical version, so just direct table lookup. I corresponds to 8, L corresponds to 11, 14, 21, 4, 24, 14, and 20. Next, add the key mod 26. The 3 here was Caesar's key. We could have used a different positive integer for the key. In this case, 3. And we'll just add position by position. Mod 26 addition. So 8 plus 3 is 11, 11 plus 3 is 14, 17, 24, 7. 24 plus 3 is 27, and remember we're doing mod 26 addition, so 27 mod 26. If I take 27 and divide by 26, the remainder is 1, and then 17 and 23. And then if I wanted, I could convert this numerically coded message back to Latin letter text. So LORYHBRX. So now instead of telling a person in your second grade classroom, I love you, you could just say Lorich Brix or something like that. And if the person next door in the seat next to you who is trying to intercept this message got a hold of the slip of paper, all they would read is this and presumably wouldn't know what was being said. Of course, it's important in second grade to keep the other kids from knowing that you're sending these secret love messages, otherwise they make your life miserable. So suppose you send off Lorik Brich to your next door second grade neighbor, and he or she writes back Junior Dizzy Dib like this. Question, what was said? Well, what was the response? Well, let's convert this to corresponding numerical equivalents like this. And then if you add the key to encrypt a message, to put it in coded form, you should undo that operation. You should subtract the key to decrypt or unencrypt the message. So key of 3 and subtract. Again, mod 26. So 6, 14, 0, 22, 0. And here is something worth discussing. 1 minus 3. But remember, this is mod 26 addition. And so 1 and 27 are the same number, mod 26. And so now when I subtract 27 minus 3 is 24. This is sort of like borrowing, so to speak. And you may have done something similar if you've done time of day calculations. Like it's 7 o'clock, what time was it 14 hours ago? So it's a 7 minus 14 type calculation, but you can use the fact that clock addition is done mod 12. Here we're talking mod 26. So then I take these letters or these numerical codes and convert them back to the English message and get the distressing response to my I love you message. I hope you had better luck. How about here? Decode this message. Something to point out. Again, we commented that the key 3 could have been replaced by something else. I can use a key of 6 or a key of 13 or a key of 7. And a key of 0 does nothing, and so mod 26, actually I have 25 possible keys. I could use 1 through 25. And the key, once somebody knows that this system is being used, the key is the only security that you have. If you have the key, then you are able to decrypt any message that comes along. This message may have been sent by someone else, and so the key is not necessarily 3. In fact, let's think about it a little bit. Maybe you've done crypto quips, I think they're called, in newspapers, where a message like this is given and one letter stands for another. You don't necessarily know which letter stands for which letter, and your job is to decrypt or crack the message. For cases like that, you use grammatical clues to help decide what the key might be. So now you're thinking about being Eve herself and breaking this code. And perhaps the biggest clue you have is here is a letter that is apparently a single word by itself. There are only two of those in the English language, only two one-letter words. They are A and I. And so thinking about the possibility that G is an A or that G is an I would be very good strategies to try. If G is an A, then I look at it and say, well, those are 1, 2, 3, 4, 5, 6 apart. So let's try to decrypt this message with key equals 6. And so now I'm not going to do the entire calculation. Let's just show how you would start it, and then I would suggest that you do this to get some practice. So J-O-M is going to be the letters 9, 14, 12. And then with a key of 6, and I'm decoding, so I subtract, and get 3, 8, 6. And then I convert those decoded numbers back to letters. 3, 8, 6 is D, I, G. And that's comforting. The first 3-character block here apparently is the word dig. This one we already decided was the word A, at least we thought so. And it looks like this is going to work out. So if you want practice, you can take this string of letters, convert them to numerical equivalents, do subtraction of 6, mod 26, and discover that the message is dig for treasure under a big oak tree. And that's how a Caesar cipher works. Let's talk about the security of such a cipher. Remember, the whole point is to keep Eve from being able to listen in on Alice and Bob's conversation. So imagine we're Alice and Bob, and we know that Eve is going to try to be eavesdropping. And we now have some idea of what strategies Eve might use to try to break the code that Alice and Bob are using. So let's think about being Alice and Bob and saying, what can we do to make our code more secure so that Eve cannot break it and listen? In other words, when designing a code, what countermeasures could be taken against the following methods of breaking code? What if Eve decides to use grammatical patterns, such as 1- or 2-letter words? That's what we did in the example where there was a 1-letter word. We decided that that was either an A or an I, and so that meant there were only a couple of keys we had to try. Or there might be other patterns. For example, many English words end in ing, and so if you see lots of similar 3-letter patterns ending words, then you might decide that combination might be an ing. What can Bob and Alice do? They can omit punctuation. For example, if I write this, string of letters with no spaces, you have to look at it a little carefully, but if you do, it's easy to see that this says, I love you, do you love me? But if after this was encrypted, then it's a string of letters, encryption letters, that have no spaces in them, and so no longer can Eve use facts like I would have been a single letter word. the words are shoved together. There's no clue about length of words and common word endings because it's not clear where the words start or begin. So this is almost always done, and then quite often the sequence is artificially blocked apart just for readability purposes. So for example, perhaps we decide to use 5-letter blocks, and so it would look like this, and if I really wanted to finish with 5 letters in the last block, I could add a dummy letter at the end. And so I could send these 5-letter blocks without grammatical clues being offered to Eve. Another thing Eve could do would be to just keep trying keys until one works. If you look back at how Caesar cipher works, again, the key is everything in terms of security, and we commented that there are only 25 possible keys, so Eve could simply try them one at a time patiently until she found the one that works. What do we need to do? Use another system that has many more possible keys. Instead of 25 keys, how about a system that has 25 billion keys or 25 trillion keys? Computers are very patient, and they can be trying thousands or millions of possibilities per second. We need to have a gigantic number of possible codes or possible keys in order that a brute force attack like that would not be able to succeed. A third way that Eve might use to try and break the code is to use frequency of letter usage. Remember this chart from when we were talking about how Morse code was developed? And so one possible strategy for solving a cryptocrypt like this is, especially if the message is long, is to look through and see what's the most commonly occurring encrypted letter, and then come to this table and say, I'm seeing lots of a certain letter. That letter probably corresponds to E because E is the most commonly occurring unencrypted letter. And likewise, if I see lots of another letter, that might be a T, and so on. So this frequency of usage is another way that Eve can use to try to break a code. And what can Bob and Alice do about that? Use a system in which a given letter doesn't always encode into the same coded letter. For example, if I write I love you, what we'd like is some sort of system that perhaps this O gets encoded as a T, but down the road somewhere this O gets encoded as a J. I'm just choosing these letters for purposes of illustration. But then when you have this string of encoded letters, it's not possible to look back and say, oh, I think that a certain letter is an E and another letter is probably a J or a Q, because it's not used very much, because the unencoded letters themselves are encoding differently. Okay. So let's take a look at a system that does exactly that. It's called a Vigenère cipher. And though section 17.4 contains other schemes as well, you're only responsible for the Caesar cipher and the Vigenère cipher that we're talking about here. So let's do a contrast of Caesar cipher with Vigenère cipher. Remember, this is how Caesar cipher worked. You take the numerical versions of the unencoded message, you add the key, same key to each letter, and get the coded letters, convert them to Latin letters if you want to. Visionaire cipher. Suppose the message is the same. Here are the numerical equivalents. In a Visionaire cipher, instead of a code letter or a single letter key, you have a code word. If I'm sending I love you, then the code word roses might be a good choice. Now I take that code word and I go back to my table of letter number equivalents and write down the numerical values for each of the letters in the code word. So it's 17, 14, 18, 4, 18. So when I want to encrypt a message, I write down the numerical versions of the uncoded letters, and now down below here I copy the code word repeatedly. So 17, 14, 18, 4, 18. And the code word is finished, and the message is not finished, so I just start over. 17, 14, 18. Okay, I'm not finished, but I'm with the code word, but I'm out of message, so I get to stop. And now we do the addition mod 26. So 25, 25, 6, 25, 22. Here is 24 plus 17. That's 41, which mod 26 is 15. If you take 41 and divide by 26, the remainder is 15. Here is 28, mod 26, that's 2. And here is 38, mod 26, that's 12. So coded message would look like Z, and then ZG, ZW, and then PCM. I could have blocked this, as we said, to hide the spacing of the words. In this case, I'm not bothering to do that. Point being, though, notice that this is doing exactly what we commented. Here's an O that's being encoded as a G, whereas here's another O that's being encoded as a C, and so you cannot look at these letters and use frequency of usage to decide which letter might have been coming from an E or from a T and so on. So here is a example for you to practice. Again, I won't work it all the way out, but what you would have to do is take the letters, find their numerical equivalents, 22, 19, 5, 11, 22, and so on. The key is the word ambush. And so if I use the table to find numerical values for that, it's 0, 12, 1, 20, 18, and 7. So down below here, I start writing those. And I'm not finishing the rest. Then I can do mod 26 subtraction, 22, 7, 4. Again, this 11 mod 26 is the same thing as 37, and then minus 18. This would be a 17. And something doesn't seem right. 0, 12, 1. Oh, sorry, there's a mistake here. This is 20 and 18 and so on. So 5 minus 1 is 4. Now 37 minus 20 is 17 and a 4 here. And so this starts out W, H, E, R, E. And the process could keep going. If you do this for practice, you should end up with the message, where is your Nerf gun? At IWU, you may remember some zombie games that were taking place last year. All right, that's what I have to say about cryptography, and let's go on to the other topic that is in section 17.5, dealing with logic. This also has to do with the mathematics related to computers, but it's broader than that. It's also the background of our way of thinking. So in fact, logic is part of math. That's why we're studying it. It's certainly also part of computer science. Computers use logic, computer programs use logic throughout, and it's also a part of philosophy, both currently and historically. Philosophers in the time of Christ and before the time of Christ were doing logic in some ways similar to what we're about to discuss. Example that we'll come back to later are the sentences, if I am late for class, then I will not impress my mom, and if I impress my mom, then I was on time for class, saying the same thing. In other words, if one of these is true, must the other one also be true, and if one of these is false, must the other one also be false. Let's come back to that question later and build some background before we get there. Let's say that a statement is a sentence which is either true or false in a way that we can agree on, but not both. Here are a number of sentences. Let's answer the question, is each of these sentences a statement or not? So the question is not, is the sentence true or false? The question is the sentence a statement by this definition? Sentence 1, is there a Tyrannosaurus Rex in the hallway outside this room right now? This is not a statement. It's in fact a question. It doesn't try to convey factual information. It's asking for information. Number 2, there is a T-Rex in the hallway outside this room right now. That's making a claim. If there's any doubt, poke your head out the door of the room that you're in and see. And you probably wouldn't see a T-Rex. I hope not anyway. So this is an example of a statement. Almost certainly happens to be a false statement in this case. My T-Rex is better than your T-Rex. Back in the days when I was in school, we didn't have dogs and cats for pets. We had dinosaurs, and so on the playground you'd tease another kid by saying that my T-Rex is better than your T-Rex, or my Brontosaurus is better than yours, something like that. Is that a statement? Answer, no. And the problem is here, better. Nobody has said what better is, and so I might say that this is true, you might say this is false, and neither one of us has a better claim than the other. And so since we can't unambiguously agree that it's true or false, it's not a statement at all. If you own 2 T-Rexes and I own 3, we have a total of 6 between us. Again, the question is not, is this true or false, but is it a statement? And the answer is yes. We can all agree that this sentence is false. Therefore, it's unambiguously false, and it's a statement. If you own 2 T-Rexes and I own 3, we have a total of 5 between us. Yes, that's another statement. This one happens to be a true statement. If you have X T-Rexes and 2 die, you have 3 left. You say, what's X? That's the point. If X is 7, then this is a false sentence. If X is 5, then this sentence is true. And since we don't currently know what X is, we're not going to be able to agree ahead of time on whether this is true or false, and so this is not a statement. Depends on value of X for its truth. Whether it's true or false depends on the value of X. Finally, this sentence is false. Think about it a little bit. If this sentence is true, then it's false because it says it is. But if this sentence is false, then it's true because it's false and it says it's false. All right, this is a dilemma that's actually well known in logic. If this is true, then it's false. If it's false, then it's true. And for a sentence to be a statement, it has to be unambiguously either true or false, but not both. And so the way out of this dilemma is to say this is not a statement, and so we're not going to talk about cases like this in the further discussion. There's a lot of historical significance in this example, but I won't go into that right now. Okay, in algebra, the letters, say x, y, z, and other letters, are used for numerical variables. So eventually, after you solve a problem, x might turn out to be 13, and y turn out to be 7, and so on. Let's talk about a branch of logic called symbolic logic, where we also use variables, letters like p, q, and r, and those are used for logical variables that can stand for statements. Here's an example. We can say that the sentence, "It's raining outside," which actually is a statement, will be represented by the letter P. And the statement 2 plus 3 is less than 4, that happens to be false, but it is a statement, can be represented by the letter Q. All dogs wear raincoats, represented by the letter R. So I have statements that I can refer to by P, Q, and R, and then I can start talking about so-called connectives. P and Q, Q or R. The kinds of things that we use in everyday English. Here are the connectives that we will end up using. Negation, not something is not the case. And in mathematical symbolism, we use the tilde symbol. On the keyboard, most keyboards, it's the shift of the character in the upper left-hand corner, if I remember right. But we'll just write tilde P, read this as not P. Conjunction, P and Q, statement P and statement Q is written this way. P, the and symbol is the caret, like this. A disjunction is an or statement, P or Q, and you take that caret symbol and flip it over, looks like this. And then P implies Q, or also read if P then Q, and it is written with an arrow pointing to the right like this. P implies Q, or if P then Q. Let's take these descriptions of what P, Q, and R mean, and let's write the expanded form, or the English sentence form of P implies R. So P implies R is an if-then expression. And P is it's raining outside, and R is all dogs wear raincoats. So this is a shorthand way of saying if it is raining outside, then all dogs wear raincoats. Notice that P was a statement and R was a statement, and when I do P implies R and make this combination, I get another statement, a new statement. How about the expanded form of not Q? So Q is 2 plus 3 is less than 4. I want to negate that, to take the logical opposite. Well, if 2 plus 3 is not less than 4, then 2 plus 3 is greater than or equal to 4. Notice that this is also a statement, and in fact turns out to be a true statement. Q was a false statement, not Q turns out to be a true statement, as you might expect. Let's go the other way around. The symbolic form of if 2 plus 3 is greater than or equal to 4, or all dogs wear raincoats, then it is raining outside. All right, 2 plus 3 greater than or equal to 4. We just noted that that is the same thing as not Q. Or is written with the disjunction symbol. All dogs wear raincoats. That is directly statement R. And then there's an if, all of that, then, and this, it's raining outside, is statement P. So this implies statement P. Now, there's a little bit of question about order of operations here. So notice the English version makes it clear by the comma that if and then this group of information is to be treated together, and then you go on to the if-then part. So in symbolic logic, we can put parentheses around here to point out that do the evaluation of the letters, the symbolism inside the parentheses, then you go and work outside the parentheses. Finally, if it is not raining outside, then not all dogs wear raincoats. Okay, P was it is raining outside, so not raining outside then is not P. R was all dogs wear raincoats, so not all dogs wear raincoats is not R. And then it's an if-then. It's an implication. So not P implies not R is a shorthand way of writing sentence 4. Okay, let's now point out how these operations, the negation and or and implication, work. I'll try to explain this, and hopefully it'll make sense and you can just understand it. If not, then this is something that should be memorized. So these tables that I'm about to fill out are things that you should be able to recall quickly. And then we're going to use these tables actually to build other tables that build off of these. So okay, negation here. If P is a true statement, then not P is going to be a false statement, and if P is false, then not P is going to turn out to be true. So negation just takes one statement and flips its truth value from true to false or vice versa. The other three operations, and, or, and implies, work with two statements, P and Q. And so to describe how they work, we're going to have to consider all possible cases of P and Q. That's not hard to do because P can only be true, a true or a false. So those are only two possibilities. Likewise for Q. And remember our counting rule, 2 times 2 is 4. There are only 4 possibilities for the values of P and Q considered together. Here they are. True, 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 false, false, true, false, false. And here's how AND works. P and Q is true when both P and Q themselves are true. But AND means both together. And so true and false is false. They're not both true. False and true is false. False and false is false. So the AND is true when and only when both of the individual statements are true. Or, on the other hand, means at least one is true. And so true or true, true or false, false or true are all true, and then false or false is false. Finally, implies. This is the most tricky. Let me try to explain this with an example. Maybe you were one of a group of kids that had the experience where your parents would bribe you to behave well. So you might get something like, when you're a young kid, if you clean up your plate, then you can have dessert. If you clean up your plate, then you can have dessert. Let me work through this implication taking that scenario. And the question is, as I fill out these true or falses, when your mom told you that, was she telling the truth or was she not? If you cleaned up your plate and you got dessert, then Mom was telling the truth. The implication was true. If you cleaned up your plate but you did not get dessert, then your mom, unfortunately, lied to you. If you did not clean up your plate, but you still got dessert, did Mom tell the truth? This is the tricky part. Mom said what would happen if you cleaned up your plate. She never said anything at all about what would happen if you did not clean up your plate. And so this is actually true. It's not a lie. She never said anything about not cleaning up your plate. And likewise, if you did not clean up your plate and you did not get dessert, Mom really didn't say anything about that situation, and so it's true by default. You're not going to say your mom lied unless the evidence is very clear, like it is in the second case when you did clean up your plate but you didn't get dessert. She said that wouldn't happen. Again, these are things to either be understood, preferably, or memorized if necessary. Let's talk a little bit about order of operation. Let's go back and review algebra, numerical algebra. So remember how you would compute something like this. If there's a parentheses involved, it's saying do me first. And so 2 times a negative 4 plus 3 times 2. And then per order of operations, you do multiplication and division before you do addition. So the next stage would be to multiply the 2 and the negative 4 and also the 3 and the 2. And finally, then you do the addition subtraction. And so how do the order of operations work? Well, first of all, you do anything that's in parentheses. Then you do any negation. So this negative 4, for example, I put the negative sign with the 4. Then multiplication or division, and finally addition or subtraction. Okay, and this is convention. It could have been said otherwise, but we've long ago agreed in mathematics that this will be a standard order of operation. In symbolic logic like this, there also has to be an understanding about what the order of operation is. And so here it is. We take it as a given that first we do anything in parentheses, then we do a negation if it's around, then we do and statements, then we do or statements, and finally we do implications. And so on the example back here, for example, these parentheses actually would not be required. If they were removed, the implied order of operations says do this first anyway before you get to the implication. But it's not wrong to put those parentheses in. All right, let's do an example of something that you should be able to do. So it's quite likely, almost certain, that you'll be asked to do this on the test, and certainly you'll be doing some of this for homework. Complete a truth table for the statement not the quantity P or not Q. So the way you do this is to construct a table that has as many rows as you need. In this case, there are 2 variables in the expression, and each can be true or false. So as we said before, there are 4 possible combinations of truth values of P and Q. And now let's look at this and say, well, what would need to be done first? The expression inside the parentheses. But that is that has several steps in it as well. Inside the parentheses there's an or, but there's also a not. And if you look at the order of operations, not happens before or. So the very first thing to do would be to do this not Q. Okay, let's do it. Here's information about P, but I'm just worried about the information about Q. So I take Q and apply the negation operation. Remember, that just flips the truth value. So true flips to false, false to true, true to false, false to true. That's what not Q looks like in each of these 4 cases. Next, we would do the statement in parentheses. That's P or not Q. Okay, to do that, I need to be using the correct columns. One column is P, and the other column involved in this OR statement is not Q. It's right here. So now I use the first and the third columns, and I apply the logic of OR, which remember is true exactly when at least one of the two statements is true. So true or false is true. True or true is true. False or false is false, and false or true is true. Finally, after we've done the expression in parentheses, there's a negation. So we'll need one more step, one more column in the table, and that is to negate the expression that we just came up with. And so looking at this column and again applying the negation, it's false, false, true, false. So complete a truth table for this statement. The columns that I would actually need to display the answer would be the columns for P and Q, so we knew which cases we were talking about, and then this is the answer column. And it's certainly okay to leave, and good actually, to leave these columns in. It's like showing your work as you do an algebra problem. Okay, two statements that have the same truth table are called logically equivalent. And so here's a one compound statement, not the quantity P and Q. Here's another, not P or not Q. The question is, are these two logically equivalent? Are these two saying the same thing? All right, let's build truth tables for each. We'll actually use the same table, but build separate columns for each of these expressions, and then see if they are in fact the same. First, let's work with the not quantity P and Q. So I would need to do a P and Q, and that would work like true, false, false, false. Then I would need to negate that, so not P and Q. And that would be false, true, true, true. By the way, you might want to pause the video on examples like this and see if you can work out the truth table for yourself. Then I'll flip over here. Negation happens before the OR, remember, so I would need a not P expression. So now I look back at the first column and negate and get false, false, true, true. Also, there's a not Q, so before I do the OR, I had better do the negation on Q. Look at the Q column and negate and get false, true, false, true. Again, that comes from looking at the column for Q. Finally, I can do not P or not Q. So to do that, I'm looking at the not P column, the not Q column, and doing the OR operation. So false or false is false, false or true is true, true or false is true, true or true is true. And now to answer the question, I look at the columns for the two statements that I want to consider. One is here, one is here. I compare them and note that they are the same. So yes, these two statements are equivalent. Okay, so in logic, these two statements are equivalent. In English, if these P's and Q's had English statements that they were representing, then we would be saying that to say this means the same thing as to say this. Let's look at an example of something like that. What's another way to say it is not true that hippos are cute and edible? Let's apply the symbolic logic that we've just used. Here I see actually a couple of simpler statements inside. So one is that hippos are cute. The other is that hippos are edible. So let's let P stand for the statement, and it is a statement. Hippos are cute. And Q stand for the statement. Hippos are edible. Now, what is being written here? It is not true that hippos are cute and edible. How can we write this symbolically with these statements? It is not true that hippos are cute and hippos are edible. And I could, but don't need to, put parentheses, or actually I do need to put parentheses, sorry. Otherwise, it looks like the not is just being applied to the P. In fact, it's negating both the P and Q. So it's not true that hippos are cute and edible. Okay, let's look at the example that we just did. We just saw an expression in the example at the top of the page, not the quantity P and Q. Here is not the quantity P and Q. And we just showed in this example that that statement is logically equivalent to not P or not Q. So this is logically equivalent to not P or not Q. And so now let's go back the other way and take this equivalent statement and write it out in English. Not P would be to say that hippos are not cute, and not Q would be to say that hippos are not edible, and there's an or statement. So in English, we might say that hippos are either not cute or not edible. I added this either because in English when we use or for two cases like this, it's customary to put the word either in. But hippos are not cute or not edible is also correct, and people would probably understand what you mean. Notice that the word or might be used a little differently than what you're used to. So for example, if somebody asks you if you want coffee or tea, a mathematician, a logician, might answer yes, and that would be a correct answer, although certainly not the one that you were hoping for. Because an or statement is true if one or the other or both are true. At least in mathematics, that's the way it works. In English, sometimes we use what's called the exclusive or, where we mean that, where or means that one or the other, but not both are true. In mathematics, we use the so-called inclusive or statement. The or statement's true if one or the other, or both are true. Notice that this is actually different than saying that hippos are neither cute nor edible. That is logically different than saying hippos are either not cute or not edible. All right, let's go back to the example then that we started with. If I'm late for class, then I will not impress my mom. And here are three similar or related statements. And the question is, three separate questions. Is each of these logically equivalent to the original statement? Let's attack this problem with symbolic logic. I see simpler statements inside this. I am late for class. Let's just let P stand for that statement. I am late for class. And Q is can be a statement that I will not impress my mom. All right, then this compound sentence is saying P implies Q. If P, then Q. It's a direct read. Let's translate each of these English sentences into their logical statement form. So if I impress my mom, then I was on time for class. It's an if-then, so it's an implication. And I impress my mom is actually the negation of Q, so not Q. And I was on time for class is the logical negative of I am late for class. So that's not P. This is a longhand way of writing not Q implies not P. So one of the questions then is going to be, is P implies Q the same thing as not Q implies not P? Let's go ahead and find the symbolic forms for these others. If I am on time for class, that's not P. Then implies I will impress my mom. That's not Q. And finally, if I did not impress my mom, that's Q. Then I was late for class. That's P. All right, so as I said, the three questions now are, is P implies Q the same as this one? Is it the same as this one? Is it the same as this one? To do that, let's build a truth table. There are two statements involved throughout, P and Q. So I'll have columns for P and for Q. I'm building the table myself now. There are going to be a lot of columns, so start near the left-hand side. And the four cases are true, 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 false, false, true, and false, false. Now let's see what columns we need. First of all, we're going to be comparing to P implies Q. And from our rule for how implication works, this goes true, false, true, true. Let's actually put a double separator bar here. To the left of this is just the placeholder variables keeping track of which row or which case we're in. Now here's another block. I just did the truth table for P implies Q. Now there's going to be another block in which I figure out the truth values of the first sequence of statements. So to do that, I see that I'll need a not Q. That works like I go to the Q column and negate, so false, true, false, true. I'll also need a not P, and negating the P column is false, false, true, true. And finally, a not Q implies not P. And that will finish this block of work. Okay, careful here. Not Q implies not P. So false implies false. That's true, using the implication table and the way that works. True implies false? No. False implies true, that's true, and true implies true is true. All right, I'm ready to answer question number 1. I look here and here, and I notice that they are the same. And so are these logically equivalent? Yes. P implies Q and not Q implies not P are logically equivalent. Okay, let's work on number 2. I'll need a not P. Actually, I already have that. And a not Q. I already have that. And so I'm ready to go to not P implies not Q as another block. And now I'm going to use this not P column and go to the implication for the not Q column. So in terms of direction, I'm going from right to left, but that's just because of the order in which I have these two written. So false implies false is true. False implies true is true. True implies false, that's false. And true implies true is true. And I'm ready to answer question 2. Let's use this color. I look here and here, and I see that these columns are different. And so the answer to question number 2 is no. P implies Q and not P implies not Q are not logically equivalent. They're not saying the same thing. Finally, let's go on and tackle Q implies P. Again, I have the two columns that I need right here, the very first two columns, and I'm going from the Q column toward the P column. So true implies true is true, false implies true is true, true implies false is false, and false implies false is true. So then I'm ready to answer the third question. I look here and here, and notice that these are different. And so the answer to the third question is no. P implies Q and Q implies P are not saying the same thing. So notice that only number 1, in fact, is equivalent to the original statement. The forms of these examples 1, 2, and 3 were chosen for a reason. These are logical forms that come up quite frequently enough that they're given English names. So if the original statement is of the form P implies Q, then to say Q implies P is called the logical converse. And is that equivalent to the original? No, it's not. The logical converse was the case in red above. To say not P implies not Q is given the name of inverse. Notice that those two were not logically equivalent. And to say not Q implies not P is called the contrapositive, and that did turn out to be logically equivalent to the original P implies Q. So the contrapositive is saying the same thing, but the converse and the inverse are not saying the same thing as the original. You might note from the example above, in fact, that the converse and the inverse are saying the same thing to, see if I can point to the right place. No, that's not true as well. Just forget about that statement. The contrapositive is the only one of the three statements is saying the same thing as the original. Okay, and let's finish with some examples from Bible statements. There are lots of implication, if-then statements in the Bible. I'll give some here. And as we interpret Scripture, sometimes we may read something into or out of the meaning of the Bible that wasn't there. Or in particular, if you're doing a biblical translation, you better understand this logical system, or you might end up translating something that's different than the original. Galatians 5:18. But if you are led by the Spirit, you are not under the law. I could put a then after the comma and read this. If you are led by the Spirit, then you are not under the law. That's an implication. Let's let if you are led by the Spirit be represented by the proposition P, and you are not under the law be represented by proposition Q. And then this is a statement of the form P implies Q. Question, is that saying the same thing as if you are not led by the Spirit, then you are under the law? So, what is this? If you are not led by the Spirit, that's not P. And you are under the law is the same thing as not Q. And so here we're talking about not P implies not Q. Is that the same thing as P does imply Q? The answer is no. This is not equivalent to P implies Q. Okay, so to say if you are led by the Spirit, you are not under the law is not saying the same thing as if you are not led by the Spirit, then you are under the law. Those are two different things. Might want to pause the video and work out examples B and C for yourself. It looks like, okay, if you are under the law, that is not Q. You are not led by the Spirit. That's not P. So the implication being discussed here is not Q implies not P. Is that logically equivalent to P implies Q? Yes, this was the contrapositive. Is equivalent to P implies Q. So to say, if you are led by the Spirit, you are not under the law, is saying the same thing as if you're under the law, you're not led by the Spirit. You could translate this scripture either way and still be true to the meaning of the original. And finally, if you are not under the law, that's not Q. I'm sorry, that's Q. Excuse me. You are led by the Spirit. That's P. And so the implication discussed here is Q implies P. And the original was P implies Q. This actually notices the converse, which is not logically equivalent to the original. So in fact here we had the inverse not equivalent, contrapositive is equivalent, and converse not equivalent again. Last example. Same directions. Here's a scripture verse that has an implication in it. Here are some alternate forms proposed, and your job is to decide whether these are saying the same thing as the original. Again, might want to pause and work this out on your own. If you declare with your mouth Jesus is Lord, let's let that be represented by proposition P. And believe in your heart that God raised him from the dead. Let's let that be represented by Q. Then, implied then, you will be saved. Proposition, let's use R for the next Latin letter coming along. And so notice that the comma is here telling us that P and Q should be done first. So P and Q implies R. And I can, but don't need to, actually put parentheses around the P and Q. The order of operations would tell me to do that and before the implication. Anyway. All right. Is that the same thing as if you are saved, then you declared with your mouth Jesus is Lord and believed in your heart that God raised him from the dead? Okay, if you are saved, that's R. You declared with your mouth Jesus is Lord. That is P. Believed in your heart that God raised him from the dead. That is Q. And so this implication is saying R implies, there's an and here between P and Q, so P and Q. And so are the original and this version equivalent? No, this happens to in fact be the converse. So Romans 10:9 says this, that presumably we accept as true since it's in the Bible. This is not the same thing, and so this may or may not be a true statement to make. If you do not believe with your mouth Jesus is Lord, if you do not declare with your mouth that Jesus is Lord, that's not P. Or, do not believe in your heart that God raised him from the dead, that's not Q. Then you are not saved, or you will not be saved. That is not R. Oops, not R. So here we're talking about not P or not Q implies not R. All right, is that saying the same thing as the original? I'll let you think about that a moment, and let's go to the last example. If you are not saved, that's not R. Then you did not declare with your mouth Jesus is Lord, that's not P. Or did not believe in your heart that God raised him from the dead, that's not Q. And so this is saying not R implies not P or not Q. All right, what about the answers to the questions then? Well, note one thing, that not P or not Q we showed earlier. Let's see if we can find that. Not P or not Q is logically equivalent to not P and Q. So this is the same thing as not P and Q. So though the statement was, part B was written as this, it's the same thing as this, and then the question is the expression in black here the same thing as the original? And making lots of typos here, sorry, this should be a not R. Is this logically equivalent? Well, I've negated both and kept the order. That in fact is the inverse, and it is not equivalent. Finally, let's go to the last one here. Again, this is the same thing as not quantity P and Q. And here is the quantity not R. So is not R implies not P and Q the same as P and Q implies R. This is the converse, and it is equivalent. All right, so that finishes what we have to say about logic. Again, used both in history and currently in philosophy, computer science, and mathematics. Thanks.